Alright, so I was just about to go to sleep, but this fun question got posted in the OECH, and I'm going to literally just try and solve it on the spot. I have seen it for a couple of seconds. I have some ideas for how to solve this, and there are two interesting things about this. Firstly, I'm just going to try and solve it in the way which springs to mind first, which is basically there were lots of things going on here. We've got let's go about the obvious way. The question is to find f of 0, 0, and trying to find that. And this is not f of 0, 0 equals that. It's f of x, y. And so the question is how to go about it. And your first step might be to say f of 0, 0 equals, and then, well, we need to find w. W is the first thing in that equation, so we say w equals square root of 2 minus, well, that's just 2 minus 0, and that's minus 0. I think I'm getting this right. Over 2. I'm doing this quite quickly, but yeah, we've got 0 minus 0 in there, minus 0 minus 0. So square root 2 over 2, we're squaring that, so we're going to have w squared equals half. And then, okay, so we know that, so we can then take a look at this and say, okay, substitute this in there. We've got w is square root 2 over 2. Substitute that there, substitute a half here, and we know x and y are 0 and 0. Sorry, it's not being multiple. There we are. And we end up with this. F of x 0, 0 equals this. Which doesn't seem all that useful because we still don't know what f is. So here is the I had a couple of thoughts. My next thought was, okay, this looks in form like what's known as a partial difference equation. It's not quite, but it looks very similar. So partial difference equations are equations of the form f of x equals f of x plus a, or some function of f of x plus a, and so, well, let's say fx minus a. And so if I know f of x, so I can then rewrite that like this. And I can then say, okay, if I know f of x, I know f of x plus a, and you can keep working more and more out based off of that. That's a partial difference equation. This looks related to that, and partial difference equations do have techniques to solve them, but there's a w squared, and the w it's not like your x and y variable, so this w is a little bit weird, and so we could maybe try and cope with that. However, this square root caught my eye, and this square root is going to tell us a lot, and I think this was what will let us solve it. I'm really hoping this will let us solve it, because I've kind of assumed it will in trying to do this. So first thing I'm going to try and break out is, let's just double check I've gotten the function right. Yeah, okay. So the first thing I'm going to try and break out here is the quadratic formula, because you notice w looks in quite a similar form. So quadratic formula states that the solution to ax squared plus bx plus c equals 0 is given by minus b plus or minus square root b squared minus 4ac over 2a. And this, we've got some similarities here. We've definitely got some similarities, so I'm going to move this around a little bit. I'm going to chuck a bracket here. Now, we're not quite there yet. It's not quite the same thing. It looks very similar, and it's this similarity which is enticing me to think we might get something with that. And also, these, the plus w and minus w, that feels almost as though we've expanded something out of the form x, I don't know, something plus w and y plus w, and we're going to get one term with x and w, one term with y and w, something like that. So those are my initial thoughts with that. So we're gonna look at this. We're gonna see that it doesn't actually quite match up. So what would we want in order to, if we wanted to say that w equals this, we'd need, I'm trying to think, okay, we'd want to split this into terms. So the naive thing to do, which is what I think I'm probably going to do, is to say minus b, and this won't work. Minus b is x. Sorry, minus b is minus x plus y, hence b is equal to x plus y. But we can see from the inside that's probably not going to be the answer. We can say a equals 1. Is this then? This then gives us that, and we then need to look at the inside of this, which is going to be a little bit problematic, I think. There are a couple of ways I can see this might go, but we'll work this out. So this should be equal to b squared minus 4ac. There will be a solution to this, I think, because we've still got one free variable. So I'm going to substitute some things in, get rid of that. Okay, here we've got something interesting. We've got a difference to squares, but quite an interesting difference to squares. So I'm going to expand these out. Do I want to do anything first? I don't think so. So we're going to do x squared plus 2xy plus y squared minus x squared minus 2xy plus y squared. Get rid of both of those. I'm going to expand the minus sign inside here. So if you pull this through, and so I was hoping we'd get quite a few cancellations. Squares cancel. We're left with something that divides through, at least by 2. Minus 2c. Again, I'm rushing this, but I think that's about right. 2. Delete this. Okay, we can rearrange this. We can get something. This isn't necessarily. I don't know if I've necessarily gone down the correct route here. It's a route. So I'm gonna keep trying. So minus 1, say minus 2xy. I actually probably rearranging those like that wasn't the best idea, because I will still need to pull this back over to the other side, and I think I might have mucked something up there. Not so. Oh no, that would have been right. Okay, but anyway, doesn't matter because we're still dividing through by minus 2. Which gives us c equals that. So we're looking at an equation that looks something, there's something going on that looks something like w squared plus x plus y w minus a half xy. Now, this is quite interesting. We know that a half is something of an interesting value, especially like it's near a squared term. It's definitely related to a square term, because we've got it just in terms of, I'm a physicist, so I always think in terms of units. Like that's very, very similar to a squared term. So that's quite interesting. Let me also remember to mute Discord. So this is the solution to this equation. And I'm thinking, by comparing it with this, we might get something interesting. I mean, ideally, we might get something that looks like our solution. I'm wondering if this is going to be equal to 0. So the really difficult thing with this is just these terms. So there are other things I could think to do with these terms. So we could take this where x and y are both very small, but we're a very short distance from 0. That might be a way of solving this, because honestly, I'm looking at this and this feels like heavily related to this, but I don't see a way I can directly get it into a form that looks anything like that to get us something useful. Like, it feels like someone better than me could probably spot something there. But I'm not very good at spotting clever tricks when it comes to maths. Although, what if I... Okay, gonna try splitting this up into two terms, which are both identical to one another. Gonna try... Do I want to do that? Well, I have no idea whether I want to do this or not. I thought the similarity to quadratic formula was a lot larger when I decided to try and do this. And I now see it isn't, so I'm now very much winging this on the go. Which genuinely is actually making for quite a fun challenge. Okay, so my thought was maybe we can, in some way... Maybe we can, in some way, factorize this. And can I pull a... So the issue is it's this plus W. I think this is the thing I want to split up into two terms. So I'm going to split that up into a divided by 4, and I'm going to pair these off with one another. I'm then going to factorize out the y. And it gets us somewhere in a somewhat interesting ballpark, because this now is looking very similar to that. It's not the same, but it's looking quite similar. So, what other options are there available? Because on its own, I don't feel like this is sufficient. Might be a clever thing to notice, but as mentioned, I'm not good at noticing clever tricks. The issue is also there are multiple ways I could rearrange this. Because, like, I made a very particular decision here to say I was going to let b equal x plus y, but I could also have let b equal x plus y over 2. I did that because I knew I'd get the w squared out front if I let a equal 1. But maybe I might have wanted a minus w squared out front or something. That probably wouldn't have been very interesting. Actually, it wouldn't have been at all interesting. We'd have just multiplied all of this by minus 1 and we'd have gotten the same equation. But yeah, this feels tantalizingly close to that. Is there any way I can try and say something along the lines of this? Because I have a hunch the answer, just with this symmetry, I have a hunch the answer could be 0. Wait a second. So, my question with this initially was whether or not there was a single well-defined answer to this. Because, let's just return. Let's return to what we had initially, actually. F of 0, 0 is equal to f of 0, w. Is f of 0, y. And for values of w that look like, well, that's just half, forget, and root 2. I must admit I've been played, because I thought that seeing this would give me seeing relationships with quadratic formula. I suspect the relationships to the quadratic formula isn't coincidental. I suspect whoever came up with this problem used the quadratic formula in some way to do it. And I suspect f of x and y will turn out to be quadratic in some sense. If I had to guess. Alright, let's go back to this stage. If I'm going to make that guess, then what I can say is we've got minus, so I'm going to expand this back out, half xy, yw, I'm not actually paying attention to what I'm doing, yeah, okay, that's right. Okay, I want to make the bet that it's going to look something like this. So I'm going to add on that there. That's going to mean I need to subtract an xy. And I would need to, again, plus x. And then subtract an xy from that. That's going to get us a factor of... I don't like the 5/2 coming out. Feels a little bit ugly. However, this gives us something interesting. So for that so we can now compare these two. This is a function of that form. So if we let f of xy equal xy, this seems like it's a solution that would work. Or sorry, f of xy equals some multiple of that, because we say, okay, this is equal to f of xy. We can, this, just from that definition of w, this is a true statement. And then simply by comparing these two, we can say that, I think this is right. Oh, no, it isn't. It isn't right, but it is close to it. Feels very close. It's that 5/2 that is the problem. Because, no, I was going to say, it very much looks like f of xy equals xy is the solution, because that works for these two terms, but then doesn't work for this term. We have that extra scaling factor. Extra scaling factor of 5/2 that's going to cause us problems. Everything about this suggests to me the answer is quadratic, in some sense. I've now got a fly crawling over my screen. You guys can't see it, but I can. That just feels so close. Okay. If I want to go down a really painful route of trying to do this, I could just eliminate w. This is gonna actually be ugly. This is, for anyone wondering why I use Microsoft Word for maths, is because it's quite nice at keeping track of lots of equations when they do begin to get a little bit ugly like this, because I can just rearrange things quite quickly. This is why I do use Microsoft Word for lots of stuff I do. I'm interested in the negative root of this, because we haven't played around with when that's... So there's a square root. When you have a square root, there should always be some importance to the negative sign in front of the square root as well. That should have some meaning. So, okay, I'm going to look at this. I'm also going to look at what it looks like squared with a negative sign out front, because I think that might might possibly give some sort of hint. But yes, let's expand these out. Expand this in here, chuck that in here, chuck that in there. It's going to be squared. Negative signs cancel. Comes out. Expand these brackets because we now have nothing on the outside, so we can expand those. Chuck this inside. Chuck that's just going to come out. Looks like that. We can pull these two terms together, chuck a 2 out front of that, and keep a minus sign from that one. Alright, that should be that, I think, because that's just from the B term. Should we get that? Okay. So things I'm noting are, again, we've got a difference 2 squares cropping up. So let's just take 2. Difference 2 squares. This is going to be minus that. It's going to be 4xy. So yeah, we can just substitute this in, and I guess I can divide through by this. We do also have alternatives of making substitutions as well, which might be something worth thinking about. So that'll be a half. This will be a half. And that will just go down to that. Expand this out. This is not looking nice. But that gets rid of that. This is very, very much... I suspect there's a clever thing one can notice, which gets you further than this. Because this is an ugly way of solving a problem, if I'm honest. Yeah, I mean, this just doesn't look like any fun. What could I think about doing? I don't see much. So, there is an alternative solution, or an alternative way I can look at this. I'm gonna say none of this is probably going to be that useful, and I'm going to take a look, give an attempt with this alternative solution. So what happens? So I want to now pick a variable. I want to investigate this around the point. I want to investigate this around f of 0, 0. And so I basically want to discuss it when x and y are particularly small. So when x and y are particularly small, what does this look like? Well, this is going to look like, so I'm going to use the Taylor series here, which basically it's like, for those of you who haven't done much calculus, it's like looking at something, it's like trying to work out where a hill goes by looking at the gradient of the point, and by saying, well, I know if I take one more step upwards, I can work out roughly how high I go from that gradient. The gradient might change as I move, but if I'm taking a small enough step, it doesn't matter, and I'm going to take a step that is infinitely small. Going to do delta x. So the delta x is my step size, it's how far I'm walking up the hill, and these, so it's this is my gradient at that point on the hill. I'm actually gonna wait for a second whilst Word decides to load these in. One annoying thing about Word, just did some update, they decided this would be really slow for some reason. Don't know why. And so to do that, I'm just gonna substitute that. Okay. So for very small x and y, I can also do stuff with this, do stuff with w. So what does this look like for small x and y? Because I don't need to solve this to find f everywhere for this to work. I only need to find a self-consistent version of f nearby the solution and show that that can be grown elsewhere. So in that instance, so we're now assuming these are very, very small, and we can take the gradient of functions nearby. Okay, so I'm going to take the square root of 2 outside the front there, and this seems suspicious. This expands out to the first term in the gradient, looks like this. And if these two are very small, then when you square them, they're just going to get even smaller. So in terms of the gradient, this is actually all that matters for this function. Because remember, I'm not trying to find this function everywhere. I'm trying to find this function infinitely close. And so infinitely close, nothing else but these matters. Or at least that's the idea. So that's going to be in the limit of those going to infinity. I'm just going to use an equals. One might choose to use an approx. I'm just going to remember that it is an equality when these two are small, which is why I've included the delta outside the front of them. And so then what do I want to do? Yeah, let's work out w squared. W squared is going to be given by... That's going to be... We're going to get the... let's write this out fully. So make it a little bit clearer what I'm doing. So, okay, so this is... This I'm going to square. I'm going to bring that out. I'm going to bring the quarter out front first. Substitute this in. I'm going to do the same. Going to do the same trick as I did before, just putting... substituting things in, but we're going to note that this term has two things that are very small multiplied together. That gets something that's even smaller, and we only care up to, it's called up to first order, which is basically we're only interested in how steep the hill is, not how much the hill is curving. And so I'm going to chuck 2 out there. Pull those 2 into one term, and I can divide through by 2 again, and that's interesting. That's interesting because that looks very, very similar to W. It's not the same, but it looks similar. Any way I can make it look more similar? I could multiply through by like square root of 2 or something. That will get me an equation. Maybe it'll be a useful equation. Not certain. But for now, I'm not going to do this. For now, I think I'm going to take these equations and start working, because now we can see that W... it was close, but W isn't small, which is a problem. When x and y are small, W is not. Because even if I let x and y go to 0, W will still be non-zero. So in the limit, which is what I was trying to take, we'd get something like the following. And this doesn't help us at all. And get this, we'd chuck in this term, and we'd have something similar. Yeah, we'd have something similar to this term for each of these, except this would be around the point 0 and the point square root of 2 over 0, square root of 2 over 2, and it will be in a... I'd need to add some slightly extra terms to those to account for the deviation from square root 2 over 2 on that W. But that doesn't work. So I am kind of stumped. I'm also not 100% convinced that this equation only has one solution. Because I can write this as follows. So yeah, I'm not certain the solution to this is unique. On the other hand, I think I've just seen something interesting. Okay, so what I was going to point out is x and y. Well, I was going to point out that we can substitute all these variables in. And this equation, I don't know. It looks similar in ilk to sorts of equations that aren't unique. Like, differential equations normally aren't unique, and this has like greater jumps in them than most differential equations do. You could probably construct a nice differential equation from this, and it would potentially hold true. But what I noticed when doing this is this term. This term is interesting. One of the things that meant this wasn't a particularly nice quadratic formula was the fact that in here we have an x minus y, and out here we have an x plus y. But that disappears because y is 2y over 2. And I can then add 2y on the front of that. 2y, that's going to go into here, and that's going to become 8 minus y in there. Suddenly, hey, that's looking a lot friendlier. And I can do exactly the same thing here, and this is now going to be a y minus x. And that looks a little bit friendlier. Issue we still have to deal with is that because, okay, now they look similar, but they're still not quite close enough. Why do I get the feeling the answer is just going to be something like x squared plus y squared and it works? Because I think I know that f of x is going to be second order in this. I'm going to hazard a guess that f of x, y. This is one very, very simple way of solving more or less any equation. I'm going to guess that f of x, y is going to be in the form ax squared plus bxy plus cy squared plus I don't even know if I want to do this. I think that, okay, I'm going to add in these extra terms, but I don't know I'm going to need them. Plus dx plus ey, not Euler's number, plus f. I don't really want to do e or f. G, y, and h. Okay. Because I feel like if I just substitute this in, I might get an answer out. But the y squared, that's always going to contribute to square root. And that square root's not going to disappear when I square it. So I need something that can get rid of the square root. Sorry, the square root will disappear when I just square the square root, but I will get cross terms when I square that, so it won't help out. So that's not enough. So in terms of thinking what the form of this must look like, could f of x simply be w? That would be a tricksy thing to do. Maybe W squared. You can tell I've been reduced to guessing at this stage. The thing is, I don't even know how you would prove this is unique. This isn't like a nice equation to handle. In terms of proving uniqueness, I don't know how I would show a unique solution exists, or that there exists only one solution for f. I'm trying to think about that now, because maybe trying to show that there exist multiple solutions for f could lead to something interesting. But I don't feel I have enough information to write a proof of that. So I could consider two solutions, f1 and f2. A standard way of saying this is, okay, let's assume their difference is non-zero. But their difference is also going to be equal to, well, we can look at their defining equation. The w squared is going to cancel, but we're going to be left with, I actually need to write what they're after, don't I? Shame. I was hoping I wouldn't need to, but I very much do. f1 of x y plus w plus f2, sorry, minus f2 x y plus w, and then you do the same thing but with the plus w on the other side. And I don't see a nice way of showing that either side of this equation necessarily has to be 0. That's how you would go about proving it. But I don't see a nice way of showing that holds for everything. So, alright, here's an idea. Let's attempt to solve this along a particular line. Because actually, if I solve this along a particular line, again, that's all I need. And it might make life easier. So what happens if I do solve this along, say, x equals 0, or along y equals 0, or what I was thinking of x equals y, or x equals minus y? Is there a particularly nice line along which I can solve it? I'm really annoyed I started doing this as late as I did. Did not expect this would take me this long. So let's try fxx. Because that gets us something that's quite nice here at least. It's going to be 2x. Sorry, these are two very different things I've just written down. Okay, so w will be equal to that. Then we have f of xx equals this squared. And again, it's this square root that's always causing me the problems. So what I could just try and do... Well, actually, I think this might... Okay, I've got an idea for what I can do afterwards, which is just try and get rid of that. But I think just solving it along this line might provide a solution. Ah, no it won't. Because we won't be closed along that line. I don't think. No, we won't be. So what's going to happen if we try and solve it along this line is we're going to get this. And I'll end up having to substitute w in here. W gets substituted into both of those. Sorry, there were pluses in both of those, but I knew we'd have that minus out front. And I could get rid of, and we'll then have one of those x's will cancel with this x. Those x's will cancel with this one. And that is not going to lie along the line f of xx. Because, well, at least not all the time, because those terms are not necessarily the same. So this isn't going to be the case. But I think that might be a good way of trying to solve this. Find a line along which this equation becomes simpler. Because once I can get it into that form, that's a good start. So in which case I would need a line I would need some function y of x. No, okay, how am I going to write this? I want this to exist along some curve x of t and y of t. This just feels like I'm putting off the inevitable by making these substitutions. This doesn't feel like it will necessarily help. The issue is that that's always going to be x of t. I don't think there's anything I can do to get around that. I don't think there's any clever way I can parameterize that. Such that they always lie on the same curve, because I know that, well, I don't necessarily, so the curve could double back on itself, the curve along which this is simple, and that would make sense given this is a parabola. But for now, that also doesn't help finding a solution. I can't see a nice parameterization of that where we'd get any benefit out of doing it. Don't think. No, I wouldn't. Well, okay. I would need... Okay, I should have done this a lot earlier. Because this actually... this gets us a fixed point. I should have done this ages ago. W equals 0. When does this occur? W equals 0. This equals 0, so we can rearrange this. This should be a relatively simple rearrangement. So I'm going to... Okay, so first off, I multiply up by 2, because 2 is not 0. Therefore, I can multiply both sides of an equation by it. I can pull this across to the other side of the equation. 0. Can square both sides. Hey, we've been here before. Sides, can pull this across. And you're... we know what this is equal to. We know it's equal to that. So W equals 0. Okay, no, sorry. I was laughing prematurely at myself because I had totally misread what I've written. I thought the answer was really simple and I'd just been utterly destroyed. Okay, but I have not quite been utterly destroyed yet. Okay, this is interesting. What if we let... Because we we know interesting things happen when... Okay, we know that f of 0, 0 is equal to a half, because we've found this earlier, half of 0 by square root 2 over 2 plus f of square root 2 over 2 over 0. This doesn't feel like coincidence that there is a solution here when x equals 1 over root 2, or square root 2 over 2, y equals square root 2 over 2. So if we let w equal 0, and this isn't quite helpful. Well, I don't know yet, actually. No, this might be. Let w equal 0, x equal square root 2 over 2. So we know that if these things both equal square root 2 over 2, then w does equal 0. So this is fine. This is nice, because we're dealing with... And that's the answer. Solve w equal to 0. Okay, there we are. And then that is equal to 2 of that. The only thing which is equal to itself times 2 is 0. Therefore, I haven't solved the problem. Still haven't solved the problem, not yet. It's a first step to solving it. So yeah, we note this gives us at least a single fixed point. And a single fixed point is going to be really, really helpful. Because I can also Taylor series expand about this fixed point, actually. Potentially. Well, I mean, definitely I can. So, let's just recap. How does this work? Well, let's substitute this in. So I'm going to say x equals square root 2 over 2, y equals square root 2 over 2. I'm going to substitute both. I'm going to substitute this into this equation. I'm going to get these two terms go inside there, subtract it from one another, cancels, goes to 0. We get this in here, but the same thing for that. Those two sum up, give square root 2 over 2. So at this point, we know that's equal to w, because I just took that from the definition of w, and that's equal to 0. So we just ask what the function is at this point, and we find that this is 0. This is 0. This is 0. So at that point, the thing is equal to twice itself, therefore the thing is equal to 0. Or potentially infinity. It could diverge at this point. But yeah, this is potentially very useful, because I finally have a bit of a fixed point to work off of. Which is the first bit of information we know about this function, that at least if this function is defined here, that it is equal to 0 at this point. It's the first bit of useful information we've had. Just add a note. This is or infinity. Okay. So given that, what can I do? My thought is I'm interested in the line that connects... Ugh, still not really nice, is it? So, okay, other piece of information we have are letting... Because there seems to be this... Square root 2 over 2 seems to be a really important number for this problem. So I'm going to just throw in... Just throw in this information. So we know this is equal to 0, and we know this. And these are just things that relate square root of 2. Here's an interesting property of this function. F of... What do I want to go for? Let's say f of minus w. Y is equal to w squared plus f of minus w y plus w. Well, okay, let's actually just do this another way. Let's do substitute both of them being equal to w. Or both of them equal to, yeah, we let both of them equal to minus w. We get this equation. I so need to sleep. Oh, I really did not expect this would. Did not anticipate this. This would go on for so long. Wait a second. Do we already maybe have enough information now we have a fixed point? We maybe do have enough information to solve this, actually. Because if it were any other point, not necessarily, but we've got something useful. So let's... Oh no, maybe this... No, do I take that back? I think I possibly do. I think I do. Thought I had something. Turns out it was just a sad feeling. Out of interest, what does happen? I was going to say what happens when w equals square root of 2 over 2, but we know what happens when w equals square root over 2 over 2, because that's this equation. What happens when w equals minus the square root of 2 over 2? As in this equation above, that would be interesting. W equals minus square root. Oh, sorry. That'd have to be w equals square root of 2 over 2, because if w equals... Let's see what I get here. I don't think it'll be anything very interesting, but if I let w equals minus the square root of 2, or w... The way I say no, because I've just assumed x and y equal w independently to get this equation. But I can't let them both equal w, I don't think. Because if I let w equal x, that gives me an equation in terms of x and y. And there's no guarantee that there exists a solution where y equals w. That doesn't work. I've found a fixed point, and I can work out the behavior around this fixed point. Because near to this fixed point, w varies linearly. So maybe I attempt that. How would I do this? Okay, so I say let x equal square root of 2 over 2 plus delta x, where delta is some small amount. Y equals the square root of 2 over 2 plus delta y, where delta y equals some small amount. going to substitute that into these equations, much like I attempted to do before. Now I get something out of, so actually first off, to not do that, first off let's consider what W is near this point. So W is going to be some small value because we've taken this about a point where W is 0. And we've moved a small distance away in X and Y from W being 0. So this will be, whatever we get here will be very close to 0. This is going to be minus delta X minus delta Y, because the square root of 2 over 2 is going to cancel. Okay, I'm going to again divide that by 2, put out the square root, pull the square root out front. I'm then going to Taylor series expand this, which will give me this. That's a formula that just eventually you learn to have off the top of your head. And again, I'm doing this to first order, so I can get rid of that, because only the one will make a difference. So I'm really getting rid of this, but then only the one makes a difference. And so then this is going to cancel with these two. So nearby W is approximately equal to this. Which is nice. Substitute this in. That was the noise of my watch ticking over because it's just past midnight. I have been nerd sniped. For those who don't know what nerd sniping is, look up XKCD nerd sniping, and you will understand that I have well and truly been nerd sniped here. That's not plus y, it's plus delta x. So yeah, not content with spending my whole day doing physics and difficult maths, I'm now spending my evenings, doing maths that honestly is mostly relatively basic, but I am really, really bad. I've never been good at, like, spotting clever tricks unless there's a good physical reason for that trick to exist. You can spot clever tricks in physics problems easily, but not in maths problems. Just rearranging these as far as I can. Okay. That gets me that. I can Taylor series expand about that point, assuming it's not equal to infinity, which will get me an equation. Can maybe even take the derivative about this point and find a differential equation, maybe? I don't know. We'll see where this gets me, because this might be getting me somewhere useful. So if I find the so this is the gradient. I've got two directions in which I can walk, and this is me walking in one of those. That was bad. Square root 2 over 2. Square root 2 over 2. And partial x, and then. So that's the gradient in the x direction, that's just a way of writing it, multiplied by how far I'm stepping in the x direction, and the gradient in the y direction multiplied by how far I'm stepping in the y direction, and then this is what the height I initially start at. But the thing is, we know in this particular instance, I picked this point because we know that's 0, and therefore this is going to be equal to, okay, and we can do a similar thing this side. Doesn't this look like fun? So I could like keep doing this term by term, obviously that's not the way to find the correct answer. That's still going to be to first order 0, so that's not going to make any difference, because we're assuming we're looking close enough that the hill we're standing on isn't curved. And then, okay, so first order in the series expansion of this is going to be 0. This is actually a somewhat ugly formula to write, but I'll, because of the way because of the notation I've been using, but okay, I will. So the first term we're stepping by delta x, the second term we're stepping by this much, and that's in the y direction, because that's in the y argument here. So we're going to get that, and this is going to cancel. Should be interesting. A valid solution this had better not be f of x, comma y equals 0 for all values. No, it isn't. Good. That would have been annoying. So I just had to check up above that wasn't a solution. Substituted in. Okay, so I'm going to do the same thing here, except this time we're doing this in the x direction. And here we're stepping by just delta y in the y direction. Okay. So what do we have here? We have partial f of y by partial delta y, so I can cancel this term with this term because they're the same. And similarly, I can cancel this term with this term because they're the same. So that's going to be equal to 0. And I can then... This is interesting. Because I can then cancel that term with that term. And it's at this point that I suspect I might have been trolled. And, oh no, not necessarily, okay. And so I end up with that equals 0. I can let delta y be anything I like by just saying I'm walking some distance in the y direction. I don't like the asymmetry there. I think I might have messed something up. Is that... Why would all the delta x terms cancel? Why would all the delta y terms not cancel? Everything in this problem is symmetric under interchange of x and y. So one term should never cancel preferentially to another. So no, that just means I did mess. That means I messed something up, which yes, I did. It's a nice check. So it's in the back of your mind. Yeah, I completely messed something up. Every single term here cancels. Which is really interesting. Because that implies that the... Oh no. Please tell me that doesn't mean what I think it means. Does it? Because what that implies is that the gradient at that point can be anything. Now that could mean one of two things. But it feels like it might mean that this actually does go to infinity. Whatever else it means we've got one more piece of information. which is that the gradient at this point seems... it's certainly not single valued. That could be because there are multiple solutions and it's boundary condition dependent. And perhaps the boundary conditions still all converge. That doesn't necessarily tell me anything about x of 0 and 0, or x equals 0, y equals 0. It could also be, and that's what concerns me, that the answer we got is that it wasn't single valued, or is that it could be any. The answer we got was that it could be anything. That doesn't mean it. That feels like it's not ruling out it being infinity. And I assumed that it wasn't infinity to make that calculation. Could I have done it without that assumption? I think I could have done, because I could have just said, what is the gradient at this point? And taken the gradient of all sides of the equation, I would have gotten the same thing, so that I didn't necessarily have to assume anything about the value there to make that work. It was just that it came out with a nice value for W. So yeah, the gradient is the very least not single valued, which is interesting. I could possibly work out whether or not this is infinite from that. I don't know, I trust myself to do so. I might admit to being a little bit stumped here. I wish I hadn't deleted the equation I had earlier. Wait, can I remember it? It was W squared plus y plus W plus y x plus W plus minus 5 over 2 xy was the equation I had earlier. Okay. I'm glad equals 0. Glad I can remember that. This is my last ditch attempt, I think. Do I get anything interesting? I can't, no, I shouldn't do. But this does get me. Wait a second, I mucked up with a minus sign. There should be a minus sign there. Okay. This does maybe do a little to help. Maybe. Desperate ninja noises. Desperate ninja needing sleep noises. This gives me a way of rewriting this equation at least. Because I can say, what if g of x, y is equal to f of x, y minus xy. And I can make that substitution. Oh, wait a second. I mentioned symmetry under interchange a while ago. But I didn't process how powerful that was. That's insanely powerful. That was my earphone falling out. Okay, so first off I'm going to try this, because this might get it into a useful form. But I really missed something quite important. Okay, so this is going to... I'm going to rearrange, solve this for f of x. That's literally just going to be moving this over onto the other side. But that was designed such that these two terms would become a single term and would just be left with an xy out the front, which I thought might make this equation look a little bit nicer. G of x plus x, f of x equal to that, so that's going to be minus 3 over 2 is equal to g of x, y plus w plus g of x plus w, y. That should be xy. But there's an interesting piece of information here, which I entirely missed earlier. And that's the following. Well, yeah, let's write this. That this is equal to that. Plus half, sorry. Because what I completely missed, what's nearly mentioning, is the fact that every single part of this equation... Oh, I guess this doesn't actually necessarily mean the solution is symmetric. I think it does. So my suggestion is the solution is symmetric under interchange of x and y. Or rather, there at least exists a solution which is symmetric under such an interchange. My argument is the following. And this is not a rigorous argument, I don't think. But take a look at this. If I swap x and y in every term, get x and y, get y minus x. But hey, that's squared, therefore I can factor out a minus sign. Or I can just... Yeah, I can factor out a minus sign, let's say. So I've made this by replacing x and y, but I can multiply by minus 1 inside of this. That's perfectly fine. That's going to get me minus y plus x. That's going to get me x minus y. Which, note, is back what I had here. And addition is commutative. Hey presto. This is back exactly the same thing we had here. So again, we can apply exactly the same maths here, which states that y and x feels like it might be useful. States that yeah, this also, now we know w squared is fine, or w is fine under the substitution, therefore w squared must also be fine as a substitution. But I can then do this. And note that then, simply by relabeling the variables... Wait a second. This is bad maths. Okay. This suggests that a solution where x and y can be swapped is consistent doesn't show that any solution must have that property. Does that even hold, or did I just... Am I getting tired and am mucking stuff up? I think the latter may be the case. So yeah, I'm annoyed with myself. Oh no. Oh no, you want to know why I'm even more annoyed with myself? Because I think I may have been really, really, really close to the answer earlier. And ruled out for a completely incorrect reason. That would be painful if it were the case. So earlier, do I want to leave any of this in place? Potentially want to leave that line, I think. That line as well. It's quite useful. It's a piece of information. Okay, I suggested earlier that I thought this felt like a quadratic problem. And therefore, a brute forcey solution would be of the following form. This would be then dx plus gy plus h. Thought the solution looked like this. I then ruled this out very, very quickly because w has a square root, and therefore w squared will also have a square root somewhere within it. I completely forgot that we do get square roots on their own out from this. And I think we have enough degrees of freedom that this is a completely solvable problem. That I can literally just substitute in and find coefficients, and I think everything will cancel. Can I narrow down what I want to do? I wonder if I want to hazard a guess as to what this might be. I'm going to hazard a guess that f of x and y equals f of x squared. Sorry, is equal to x squared plus y squared. I'm going to give that a go. Because if that is the case, what do we get? Get the following. Should have seen this one. Well, I don't know if this is the right answer, but I should have seen the just realise it's all. Everything should be quadratic. And go with that. X plus w squared plus y squared. And I have a hunch that things are going to cancel. Really, I don't have w squared to hand anywhere. Okay, let's work out w squared again. I've done this rather a lot. W squared equals this thing, all squared. I'm actually just going to take out the 1 over 4. If I start this time, do this. Write it out again, paste it in. Didn't mean to overwrite that. Paste that there. Paste this here. Copy this in, substitute, get rid of the minus sign, replace that with a squared. I forgot to keep the other one copied, but that's fine because I know what it was. So that, substitute in, I'm going to get the same term out from the first term in this bracket, so I can delete that, and then the second one is going to be this term squared. So I'm going to get that. We have, yet again, this term that comes up all the time, and is, I swear, the most auspicious term in this entire problem, which is going to give me what, 4xy. That comes out to... I've now just memorised that number because it comes out... Or that factor because it keeps coming up. Okay. W squared's going to give me that. How does that bode for the rest of the problem? Doesn't bode good or bad yet. Gonna get this. Gonna notice that these terms cancel. Okay, we're then going to have... Yeah, I think I just need to substitute W in here. I need to bite the bullet on that one. W, okay, let's go. W, okay. I'm gonna take the minus. Okay, so we're adding a Y to... We're adding a Y over 2 to this. That's gonna give me that. I'm reaching the stage of let's just speedrun this and get this done and out of my life. So I think this is it. Again, so make the same substitution over here. Substitute this. I chuck a minus sign for x this time for that. Okay, do I want to do anything with this? No, I think I'm going to pull the 1 over 4 outside the front of these. I'm going to make the substitution for what w squared is equal to. I'm not going to bother putting the 1 over 4 in because I can multiply both sides by 4, getting rid of all of those 1 over 4s. I'm then going to pray to the maths cancellation gods that I get a cancellation here and everything cancels out nicely. If not, then I believe the solution can be worked out simply by doing that, but that's going to be simply by doing that, maybe by adding the argument that A equals C and D equals G, probably. In fact, I'd suggest that maybe D equals G equals 0, but I don't have a proof of that. Yeah, regardless, I'm fairly certain that way will be a way to go for a solution. But, and then I never actually finished doing all this. I took the 1 over 4 out and then multiplied everything else by 4, but I never actually removed it from inside there. Okay, so I'm now gonna... I can't believe that actually works because I was fairly certain I hit the wrong button there. Substitute that in there. Substitute this in there. Move this in that bracket. Move that again. Square comes up. Okay, this time. Okay, this isn't actually the same term we normally have. That's a plus x minus y squared. This is a minus x minus y squared. These two are both going to cancel. Where did the other one go? The other one there, okay. I'm getting petulant now. It's reached that stage of the night. The petulant ninja stage. But I'm the only ninja on YouTube who actually does maths on his channel. Because I'm a cool kid. And this is potentially very interesting. Oh no. Oh no. That's so close. I'm convinced this is the right way of going about it. I'm pretty convinced this problem is closed, but that's not the solution. This won't cancel, I don't think. Oh, I shouldn't doubt myself too early. The second term... I'm almost 100% certain this term will be almost... I can just swap the sign on the x and y. Because, like, everything else was identical in this. So I just... Oh no, that's actually... I hope that's not the case. It's going to be, though, isn't it? Let's just... I'm just going to do this fully. Oops, that's what I intended to do. Do this fully, just so I can at least say I'm fairly certain that what I'm thinking of with just guessing a substitution of a particular form will work. I'm about 100% certain the method I'm doing now won't. I think if I were to just guess the substitution of the correct form, it would work, and equate coefficients, it would work, but I don't really want to do that tonight. So I can follow it up tomorrow. Okay, we have this term here. I'm going to multiply both, it's inside a square, so I can multiply by -1. That's then exactly the same as the term with the minus sign in front of it, right beneath it. Presto, get rid of that. Okay. Yep, we still have... So there was, these terms are both identical. So we have a 2 out front there. 2x minus... yeah. So this is going to cancel. This term... well, okay, let's show this explicitly. There we are. And span this out. And then I could show this in more and more painstaking detail, but these are the same terms with a plus and minus in front of them. So I got close. I did not get close enough. It might be x plus y all squared. Do I give that a go? I feel like I'm so close I want to give it a go. But I can narrow these down and say there definitely isn't the answer. Because anything that's quadratic of this form yeah, that's not the answer. Anything that's quadratic of this form must necessarily have that be equal to 0 because it can't go to infinity. But it also can't be that badly defined at that point, can it? Did I muck up my logic when showing it wasn't well defined at that point? Possibly. But we could say that f of xy equaling x minus y all squared, that would fit at least this constraint. It would not fit this one, but it could simply be that there exist multiple solutions around that point, but we're only interested in one. And all what we need to find is one solution for this problem. If we were to let this be the solution, we're going to get some stuff that's actually quite nice. And that's not the answer, I don't think. At which point I will just go to sleep. But note that if we let this be the case, we end up with this is going to be oh, okay, no, it's not. I take it back, it could still be the solution plus w, and this will be it's actually the oh no, that should be a minus w. And this would be a plus w. Which seems interesting because here we have a difference 2 squares. Or something. It's not a difference 2 squares, it's what you get when you take a difference 2 squares, but I'm tired and don't really care anymore. What you want in a video is someone just really complaining that they're tired, want to sleep, but they've been completely and utterly nerd sniped. That's going to go to plus W, this term cancel with this term. That would then get which isn't true, because I know W squared has a square root in it. So that can't possibly be right. Anyway, with that, I've finished the video. I want to go to sleep, and I will finish this up another day. Bye.